Thank you very much. I'm very excited to speak about hypernetworks in this forum because I believe that hypernetworks are a very powerful tool. Anyone can use them in their own research. I will show many different examples. And I think that it's very important to know about this tool, and I'm very happy to share what we've learned. So what we've learned, there's been some work that we did back in 2015. Then we left it aside for a few years. We came back to it last year, and we were able to do marvelous things with it, things that I would not have been able to do without it. So I would really encourage you to try this tool out. If you have any questions, please ask. If you need my assistant later on, you want some code, you want some advice, just email me, and I will be very happy to share what I know. So many people ask whether AI is slowing down. Maybe the big discoveries has been made in the last decade, and so on. And I think that it's the complete opposite. So it's only going to accelerate more and more. And I think that we are going to get into an era that I look at it as some sort of Cambrian explosion. So the Cambrian explosion in biology was a period in which there was a lot of evolution going on in a short amount of time. And I believe that this is exactly what we are going to see with deep neural networks and AI in general. And the reason that I'm so optimistic is because I see what we're able to do with unsupervised learning, with new types of supervised learning, such as hypernetworks and so on. So I think that every year we are becoming smarter, we know more tools, we have access to better technology, and we're able to do things that a year ago were not possible. So this is exactly the kind of tool that I would like to discuss today, but let me go back to 2015 and discuss a problem that we had back then. So the head of the school, Yehuda Afek, came to me and said that he bikes to work every day. He doesn't want to get wet. He wants to predict the weather. So the way to predict the weather is that we look at the rain radar images, and we want to predict the next frame. So the input is basically some frames of the radar, and we want to predict the rain in the next hour or so we wouldn't get wet by some unexpected rain. So this is basically an image-to-image type of regression problem. We have images on the left, we have an image on the right, we need to map between them. And today it's not a huge deal, we have technology for image-to-image mapping, but in 2015 technology was not that evolved. And what we noticed is that the shape of the clouds changes rapidly, and that the motion is unpredictable, and we could not solve it very efficiently with the existing technology. So we came up with something that we call the dynamic convolutional layer. So the dynamic convolution layer is just like any convolution layer, only that the weights are not learned during training. The weights are determined by another network. So this is the input. There is a network here. It determines the convolution weights. And then when moving from one layer to the next, we apply the weights that we get from this network. So instead of learning the weights during training, we train a second network, and this network predicts the filters that we are going to use in the convolution. And at that time, the architecture was pretty simple. The weight predicting network looked like this. It basically predicted 1D convolutions. So 1D convolutions, you can think of them just like shifting motion. So the first network predicted locally the shift at every location, and the second network applied the shift that the first network learned and basically moved the clouds this way. And when we apply it, we see a very nice improvement across data sets. So we were very much encouraged, but we didn't touch this technology for a few years. During these years, many people tried all sorts of dynamic convolutions. For example, in image enhancement, in action recognition, and so on. We left it aside. But the idea has been evolving. So for example, in 2017, the term hypernetwork was coined. Basically, it was coined in the domain of recurrent neural networks in a paper in iClear 2017. Basically the same idea. You have one network that learns the weights of another network. And then it was discovered again for NLP by using dynamic convolution in 2019. And there are other works as well during this time that started to work about the same idea of discovering that convolutions can be dynamic. We came back to it in 2019 in a problem that is the 3D reconstruction from a single input image. So the input is a single image, you can see it here, and the output is a 3D model. And I really like this problem, not only because hypernetworks solve it in a great way that is state-of-the-art, I also like it because it's a great place to explain the idea of hypernetworks. And it's not obvious how to use hypernetworks here, but where we use it is to represent a 3D shape. So let's think for a second, how can one represent 3D shapes? So we can, for example, we can use voxels. What is the problem with voxels? In image you have pixels, so even if you have a lot of pixels, it's still a matrix of a reasonable size. In 3D, you have a really difficult problem with resolution, because whatever resolution you add, it's to the cubic, and you very quickly have very large memory consumption. So you might say maybe have another representation, maybe point clouds. Point clouds are great, but A, they don't have topology, and B, you have a set. So basically the number of points can change. And if the number of points can change, it's kind of challenging to represent it as the output of a neural network. You can also try to have a mesh. Mesh is very easy to work with from the computer graphics point of view. It has topology. But then again, we also have the problem that it's not very clear our network, our neural network, can output a mesh. There are solutions in the literature, but it's challenging and it's not a natural representation. Parallel to our work, the idea of implicit functions came to being. And in this idea, you represent a shape by a classifier. So you have a 3D shape, and you have a classifier G that represents the shape. What does it mean to represent the shape? For every pixel x, y, z in 3D, the function G tells you whether it's inside the shape or outside the shape. So again, you use a classifier G to represent the shape. The classifier tells you for every input, which is just 3D, 3 coordinates, it tells you inside or outside. It's a binary classification problem. Every shape is a different classifier. So how can you make it such that the classifier depends on the actual shape? The way that it is done, for example, in CVPR 2019, is by using embedding. So the input image is embedded in this vector. So you have another function, the function R. This is an embedding function. And this function R takes the input image, this input image, and comes up with an embedding. The embedding E of I. So we have an index I because it comes from image I. And then we concatenate this embedding to the x, y, z, and we get a behavior that is adaptive to the input. Every image I would create a different function G. Now this is not a hypernetwork. This is an embedding type of conditioning. Conditioning simply means that you have another input. And you can kind of make 3D reconstruction with it, but it's not very successful. So if, for example, you run it on ShapeNet, then you would see that the results are not competitive at all. ShapeNet is the #1 benchmark for 3D reconstruction from a single image. So our idea is, and let me just say that this x, y, z, this input that is just 3 coordinates, we would call it P from now on. So our idea is to do metafunctionals, which is basically the implicit functions combined with hypernetworks. And the way that this is done is just these two equations. So if there's anything that you need to take from this presentation, it's just these two equations that you see here. Let's go through these two equations. So there's the network F. The network F is the network that predicts the weights of network G. So the input to F is an image I, and F has some trainable parameters, theta F. These are learned during training. And given an image I, this network F returns theta I. What is theta I? Those are the weights of network G for image I. So for every image I, we would have a different set of weights, theta I, and then G would use these weights, and for every point, it would give the probability that this point P is in the shape that is defined by image I. So let me explain again. So in the embedding-based method we saw before, we concatenated the two inputs. In this case, the inputs are not concatenated. You can think of G as a template. It doesn't have any weights. It's just a template of a network. And then you take the weights theta I, and then you get a network. You apply this network to P, and you get its probability. How do you train it? It's very straightforward. You just use the log loss, simple binary loss for classification, and you get the loss term, and then you just use automatic gradient modern frameworks, and everything is being done magically. So basically, during training, you don't fit the weights theta I directly. You learn the weights of F, theta F, and then these weights are learned with this very simple loss, where you know the binary label for every point in 3D P. You know whether it's inside the shape or outside the shape. You go over all the different points. You apply the binary cross-entropy loss, and you get the loss that you learn with. Very direct way, and only these two equations. So it's really not hard to implement. It's very trivial to implement. You just need to make sure that these weights, theta I, are the weights that get into network G. And there is one more trick that we do. The 3D space is kind of huge. We try to sample uniformly in this space, but the other half of points we sample very near the boundary of the shape, so we have some sort of biased sampling that allows us to learn more efficiently. So let's look a little bit at the architecture of this system. So we said there are only two equations. There is the network F that predicts the weights, and there is the network G. So the network G is actually a small network because it maps 3D coordinates, just a vector of 3 numbers, into a binary decision. So it's a simple function. It just, 3 layers of a fully connected network would be fine, each with a very small hidden layer. So the number of units, the number of weights that we need to learn in this network G is really not a lot. And this is an advantage, because the weights of G are going to be learned by network F. So it's actually working better for us to have network G smaller. And network G, again, maps these 3D coordinates to inside or outside. It cannot be too complex. And then we have network F. Network F maps an input image to the weights of network G. So when we say weights, we mean the weights and the biases, and the way we actually learn it, that we learn the scale of the weights independently. It gives us better convergence. So network F is something that maps an image to a rather large vector of weights. It's not a huge vector, it's a couple thousand, but still a vector of weights. And for mapping images to any entity, we have very good technology. We can just use, for example, ResNets. So F is a deep ResNet. Each one of these is a block with multiple layers, residual layers, that goes from the input to the weights. F is a very simple function, small, fully connected network. The results that we get using this, really, to implement it, is just maybe 10 lines of PyTorch. The results that we get are state-of-the-art on this very competitive benchmark that is called ShapeNet. And there are many different types of ShapeNet benchmarks, depending on the number of views, the angles that are being used, and so on. In each and every one that we tested, we are state-of-the-art by some margin. And let me just emphasize a few points. The first is that in our work, we just train one model for all different shapes. So if you look at the competition, for every category, they train a different model because they want to do better. In our case, we just need one function F to model everything. So this is a huge advantage. The second is that if you look at the literature, many of the solutions have a pre-trained ImageNet network when they start to work with the images. We don't use it. We train the residual network F from scratch, don't use any pre-training. And the third is that hypernetworks are really necessary. If we use the embedding method, then results are not competitive. They're not even competitive enough to put on this slide. And there are other advantages as well. So if we look, for example, at network F. So network F maps the image to the weights. And it has a fully connected layer here and here. Basically, just like what we do in face recognition, in object recognition, in other domains, we can look at this vector and call it the representation vector, or the latent shape representation. So imagine that from this information, you need to do regression to the weights, and the weights define the shape. So this vector here, the activations over here, must contain information about the shape. So this is information we get for free. We train the network to do 3D reconstruction, and we get this vector. But this vector is very useful. If, for example, we do TS&E, which is a form of dimensionality reduction to 2D, just to visualize, what we get is a very good separation to classes. But in our system, unlike others, we didn't condition on the class. So this information emerged, and we get the class information for free, embedding in this latent space over here. We can do something else as well. We can take the implicit representation of two different shapes, and we can just linearly interpolate between them. So this is what you can see here. This is linear interpolation. Sorry. So we can very smoothly interpolate between this space shuttle, which is one category, and this truck, which is a completely different category, and get shapes. How do we render the shapes? It's very simple. Once we have a new representation, an interpolated one, generating the weights, it's just linear regression. And then we get the weights. The weights define a function g, so we can render the 3D shape in between. And the technology is very versatile. We can, for example, use it for what is called differential rendering. We don't need a 3D model during training. We can train using multiple viewpoints of 2D. We can use it for super resolution. If instead of a G that maps a 3D point to a coordinate, we map a 2D image to a color, for example, and so on. So the technology is versatile. We can use it many different applications. Very easy to also extend it. This is something else that we did for dynamic 3D shapes. With just 2 lines of code, you can get higher dimensions, and so on. So I guess that you understand the idea of hypernetworks now. Let me show you another example that is also good as as something that we can learn what are hypernetworks from. So this is a completely different work done with Professor Raja Jairis from the Electrical Engineering School and his student Yoav Chai. And the goal here is to retouch images. So this is the input, and this is the output. And this is the input image, and this is the output. And we can solve it in a supervised way. We have some expert doing retouching, and we would like to mimic this expert and learn automatically how to retouch the image. So the way that we do it, there are many different projects out there that used image-to-image mapping and so on. We want the simplest way. The simplest way is basically to change the color space. These are the RGB coordinates. Every point in the color space is being mapped to another point. And the way that this is done, following previous work, sorry that I don't have the citation here, I should add it, is to take the RGB values of every pixel and then map them to new RGB values. So this is the input RGB values, and this is the output R tag, G tag, and B tag. And the way that this is done is that we take these vector of 3 numbers, we inflate it using second-order polynomials to a vector of 10 different numbers. This is this number over here. We just take R squared, G squared, RG, and 1. This is a vector of 10 numbers. We multiply it by a matrix that has a size of 3 times 10. And we obtain the new color. So for every pixel individually, we take the color, we inflate it, we multiply by a matrix, we get the new color. And so this is a very simple transformation. The question is, which transformation do we want to use? Obviously, this transformation depends on the input image, on the correction that we need to apply. So what we do is, given an input image, we apply this transformation that is determined by a matrix of 30 different numbers, 3 times 10. But this matrix, is a function of the input image. So we have a convolutional neural network that determines these parameters. So if you would like to use the language that we had before, then the transformation is the function G. And this CNN is the function F. Basically, it learns the weights of this transformation. In this case, just a linear transformation in some inflated space, but still can be seen as the weights of a network. So this also has the structure that we have one network F that learns the weights of another one that does the actual work. So we can apply it, and although we learned it for images, it actually works pretty well to video. And this is, for example, Game of Thrones Dark Episode. We can get very nice results of improving the lighting of the scene. And this is another set of images from the turn of the century, where we basically retouch them automatically. And this is a commercial software. This is the Adobe Lighthouse. Let me now turn my attention to something completely different. And this is another topic that we care a lot about. This is the topic of explainability. So what is explainability? There is a criticism of deep learning that we basically learn models that are black boxes. And then these black boxes are hard to understand. Maybe they are a little bit biased against a part of the population. Maybe they learn something that is superficial, but nobody understands what they are learning, and so on. So there's a very huge emphasis going on right now on explainability, knowing what the network is actually doing, what the network is up to. And we wanted to have a solution for a recommendation system. So what is a recommendation system? A recommendation system is a method that, given your past preferences, so for example, you saw 3 movies, and you gave it this rating, and you know for every movie what is the average rating, you know the genre of this movie, and you know the rating that the specific user gave, and you want to predict for this specific user whether the user is going to like other movies. What's the rating that he is expected or she is expected to give to these movies. And if you want to have explainability, you want to have something like, you're going to like this movie because other users like it, it has high ratings, and it's not an action movie. We noticed that you don't like action movies, and so on. So this is what we mean by explainability in recommendation systems. We give you the rating, and we give you a reason why this rating is the one that you would choose. So this way you know that the rating is not based on your gender, on your race, or something else, and you know the logic behind it, because maybe I do like action movies, maybe I want to change the rule a little bit, I want to edit it maybe, and so on. And the way that we do it is basically for every user we define a tree. So a tree is the most explainable machine learning model there is, because there are decisions. If there is one decision, you go left. If there is another, you go right. You get simple logic rules. Anyone can understand them. So given this tree, we are able to build these very simple explanations per user. So we said that we want to have a tree per each user. The problem is that in order to learn such a tree, you need lots of examples for a learning algorithm to apply. So if you want to use a tree learning algorithm, the one that would give an examples would give you a tree, you need a lot of samples. And for each user, you only have a handful of examples. So what you need to do is to share information between the users. And the way that we do it is that we replace the tree with the tree learning algorithm. We replace it with a network. So instead of using a tree learning algorithm, we use networks that construct the trees. And the advantage is that in these networks, we put all the information about the problem. So in this case, the function g is a tree. The function f is what builds the tree. And I'm not going to get into the details because I have some other applications to show you, and I would like to give you the opportunity to ask questions. But at the end of the day, the tree is being built step by step by a network F and not by a learning algorithm. And what we get at the ends are trees that are as competitive as some of the best collaborative filtering algorithms, which are the algorithms used for recommendation systems, but which give you explanations. So let's move again to something that is completely different. Let's talk about error correcting codes. So what's the connection to error correcting codes? So error correcting codes, the way to decode them is using message passing algorithms. And then there was this idea a few years ago by another professor at Tel Aviv University and his student Elia to use neural networks as the message passing algorithm. So neural networks that operate like this are many times called graph neural networks. They operate on a graph, they have learned weight, and this improves. The idea that we have here is to have hyper graph neural networks. So to have networks such that the weights are adaptive to the input. And this indeed brings us to an improved performance on many different codes, such as polar codes and so on. We're able to obtain improved performance and get better decoding with more noisy inputs. The same idea together with Elia Nachmani, this is work done at Facebook AI Research, was applied to predicting the properties of molecules. So some of them are regression problems, some of them classification problems. The state of the art in the literature is to use graph neural networks. What we did is that we took graph neural network solution like this. This is this block over here. And we replaced part of it with the network F that learns the weights of a network G again. And we are able to get state-of-the-art results across the board. Now, we didn't just do it to one graph neural network algorithm. We actually took 3 different state-of-the-art graph neural network algorithms and improved each and every one of them. So using this HYPERNETWORK ID, we could go to any graph neural network algorithm and make it better, improve the results, and obtain state-of-the-art results on competitive bioinformatic benchmarks. Let me just show you one last example, and then we can go to questions. I truly believe that AI is going to replace engineers in the not too distant futures. And what engineers are doing is basically design. So they have a set of specifications, and they need to design. In our case, what we wanted to do is to design electrical circuits. So this is a problem in electrical engineering. If you have electrical engineering background, then you would know that this is something that electrical engineers, they teach them how to do it, they do it in real life, and so on. So given specifications, which are basically the current and the voltage over here that you get when the network, when you apply some voltage and current to this circuit. So the specifications are what you want to get to the output. And the design is actually putting these components over here. So we have the power supply, we have the 3 different components. The capacitor is one of them, and we can put them in parallel or in sequence, like we put here for the resistor. And we have the parameter of the component. So we need to place the components in a certain way. We need to select the components, and we need to have the values, like the resistant over here, determined by some design process. And this is a challenging problem. Nobody was able to solve it unless you know the design already, and then there are some methods to get the parameters. But nobody was able to successfully place the different components. And what we did over here is to apply a hypernetwork again. So like many other design problems, from the electrical circuit to the specifications, the voltage and the current, the frequencies of these at the output, this is an easy problem. This is just some algebra, you can get it. The design problem is what's difficult. It's going in the other way. The way that we did it, given the specifications, we apply what is called the multiscale ResNet. The specifications are 1D vectors, so we apply 1D ResNet to it, and we get the weights. So these are the specifications. These are the multiscale 1D ResNet. These are the weights that we actually put in a recurrent neural network. And the recurrent neural network actually places the different components. So given a certain weights, and given the starting points, then we have the type of component, we have whether to put it sequential or in parallel, and we have the value. And then the RNN basically, the recurrent neural network basically gives you the layout of the electric circuit from start to end. And the way that this layout differs based on the input is that the weights of the RNN are determined based on this input. So this is function f, and the RNN in this case is function g. And then this is trained with cross entropy, just placing the right components at the right time. And we can actually refine it a little bit by using differential simulator, where we can actually simulate the circuit that we just got, get the outputs, and then correct the values. And what we get is that we're able to place the components with rather high accuracy, even for very large circuits and much better than any other method. So let me conclude here. So we said that, at least I believe, that AI is accelerating, and that what we can do now are things that we were not able to do before. So the electrical circuits is one such design problem. What we've seen with state-of-the-art video reconstructions with very short programs, the type of results that we get in bioinformatics, and even error-correcting codes, they are all very exciting to me, and I would be very happy to answer any question that you might have. Thank you very much.
Thank you, Professor. Professor, one question that we have received might not be directly related to the presentation. It's about the rollout of the 5G network technology around the world, which has given a rise to conversations regarding cybersecurity and the implications on data. So the viewer wants to know, how do you think it will impact hypernetworks, if at all?
Okay, so let me start by the other way around. How would hypernetworks influence 5G? So in 5G, the type of codes that are being used, the error-correcting codes that are being used are called polar codes. These are exactly the type of codes that we are trying to improve with hypernetworks. So this might be the only link between what I presented and 5G networks. We are talking about, in general, we are talking about neural networks, not about cellular networks. However, the question is very important. It asks about cybersecurity and other concerns. So as we move forward, there are two types of, there are many ways in which AI contributes to society. There is automatic driving, there is healthcare, there are many things like this. But there are also other things. One of them is cybersecurity. As cybersecurity is becoming more and more of a concern, the question is, how can you use AI in order to better protect yourself? So you can think about networks that examine, for example, the code and try to identify vulnerabilities. This is something that we did. Or you can think about other networks that are doing a process of fuzzing, testing hardware or testing software for vulnerabilities in an automatic way. This is another thing that we are working on. So I see the link between cybersecurity and AI to be a very strong link, and this is something that we are going to see more and more of, type of applications of AI to improve cybersecurity. The other concern that you had is about data and privacy and so on. And here too, the latest AI methods can help. So if we are talking about things like explainability, you know why the decision by an AI system is made. If we are talking about fairness, you know what kind of data is being used and how it influences you. It's not about data that you shared a while ago and now it pops out and you are not getting the position. Everything that an AI system is deciding is going to be explainable. It's going to give you a reason why it decided this way. So these type of technologies can surely help alleviate some of these concerns.
Thank you, Professor. One question it's a little wide in its scope. A viewer is wondering if you could give maybe more examples of AI platforms and the hypernetwork play in AI platforms and how it impacts various public platforms and public utilities like healthcare, for example, or if there's any other public utility that it might beneficially impact.
Okay, so I've shared a few examples of work that we did in the last year. It's very diverse, but it's not everything that we did. So I can tell you about very like collaborations that we have around campus at Tel Aviv University that you would be surprised. So for example, we can use hypernetworks for archaeology, for example, And we have examples where we use it in order to help the archaeologists in their work. And we can use it in medicine. So in medicine, what we did is a collaboration with another professor that tries to learn the blood flow in the tiniest vessels in the brain as a way to fight diseases like Alzheimer's and so on. They have an imaging device, but it's very noisy. So the blood vessels are tiny. It's not like fMRI, which is large scale. You want to read what is going on in the tiny blood vessels of the brain. And we were able to work with them on very noisy data and actually make real discoveries on how the blood vessels contract. And we are now trying to link between these discoveries to the way that neurons work as and influenced by blood flow in both healthy individuals and individuals with some conditions. So this is another example. We have a collaboration about hypernetworks with the zoology school that is about understanding sonar vision. So as humans, we look at our vision, we understand more or less what we can see, but what can bats see, it's not very clear. So we basically do what we did here with 3D reconstruction, but we do it from sonar. And there are many other examples of these kind of collaborations. We have some collaborations about agriculture in Africa that we just started. We have a collaboration with an fMRI researcher about working with people with PTSD, trying to understand, based on fMRI, their underlying clinical condition. Basically, if somebody undergoes a trauma, whether they're going to develop PTSD, what type of PTSD, how severe it's going to be, and so on. So all these sort of applications are emerging applications of AI that we are currently involved with. I probably forgot about some of the applications, but we are very happy to collaborate with people from our campus, from other campuses, about ideas that can help both other sciences. We have been doing some work on, for example, on design of nanomaterials, and from people from other universities. For example, our work in archaeology was part of a European consortium. We also have other collaborations in humanities with European universities and so on.
Thank you, Professor. One of the last questions that I can see here is a little technical. So let me see if I get this right. A viewer has asked that it seems that hypernetworks initialize the weights of other networks, which in turn can be employed for functional tasks like regression or classification. So optimizing hypernetworks to maximize this likelihood to get target variables seems like it's done on competitive benchmarks. Are there any downsides to this approach? Is it possible that the inferences drawn from data obtained in this method could be limiting as well?
So this is a great question, and let me divide my answer to two different parts. One of them is about the inference part. Do hypernetworks generalize better than embedding methods? Do they generalize worse? So what we can see here across the different domains is that they generalize much better once you're able to train them. And we now have a theoretical work in submission that tries to understand what is the difference between the embedding method and the method that uses an hypernetwork. And we basically compare them using generalization bounds and show that you can use a hypernetwork that is much lower complexity than the analog embedding network, and this is a huge advantage. But there is a caveat, and the caveat that the question is actually pointing to very well is that you initialize the weights of the network F, and it predicts the weights of another network. So the second network G, the way that the weights are being initialized, is not with accordance to the way that we know how to initialize weights. So we have a certain practical guidelines how to initialize weights of a neural network, but in this case, the weights of G are being initialized by network F. So it's kind of biases the sampling of weights at initialization. So there are a few techniques to overcome this. One of them has been just published in iClear by another group that studies the best way to initialize the weights of network F in order to obtain uniform and well-behaved initial weights for network G. The other things are more practical, and we do them a lot. For example, if you remember, we had the weights of network G. We said that it's the weights, the biases, and the scales. So the actual weights of network G are the weights times the scales, which is unconventional, but it works better for hypernetworks. So there's the kind of techniques that are emerging that allow us to train hypernetworks more efficiently and make sure that it converges well during training. Without these techniques, it's a little bit harder, but still possible.
All right, Professor. Last question here is related to this question. It's about approaches to task-conditioned hypernetworks. So the question is, if once a target-based model has gained its task identity, would continual learning be more difficult or less difficult as a feature in those? And furthermore, there's a postscript to this question, which is, if it turns out at the end of gathering sample data that the generalization was wider than it was anticipated, is it possible to retroactively fix this problem without messing too much with the input-output relations of the previous data?
Okay, so I must say that the question is kind of complex, and I'm not sure that I understood the entire question. But let me say that, in general, that I believe that hypernetworks better generalize than other techniques. And let me give you an example. If you think about the ImageNet type of work, sorry, the ShapeNet type of work that we did in 3D reconstruction, then we were able to use just one network to all different classes. Whereas the conventional methods used one network per each one of the 13 different classes that exist on ShapeNet. So this really tells us that we have a very high capacity in the network to capture a lot of the underlying phenomena without this added conditioning, without telling the network, now it's a chair, now it's an airplane, and so on. And this is a very attractive property of such hypernetworks in practice, that they have the capacity. If you think where the capacity comes from, it's that you're able to apply dynamic weights to G. So basically, you have a huge amount of expressivity. This is exactly what we are trying to model with the theoretical work that I was telling you about. If you think at the last example, the one of electrical circuits, then we tried to use state-of-the-art recurrent neural networks such as GRUs, orthogonal RNNs, all sorts of different ways to generate electrical circuits. They all failed rather miserably. And hypernetworks really gave a huge jump in performance in comparison to these methods. So there is something about hypernetworks, about their ability to model complex phenomena that is more powerful than other techniques. And I think that we are going to see more and more of this. And this is what I really like about hypernetworks. Not just that you get better performance. So every new method gets better performance. But in this case, it's either a jump in performance in comparison to much simpler, if you look at the lines of code, it's much simpler solution. And in some cases, you're able to do things that you were not able to do before. So with conventional networks, you cannot find a solution, and then you apply hypernetworks, and all of a sudden it starts to learn and to converge. So I believe in this technology. This is why I'm so excited to share what I've learned about this technology. I think we are only starting to understand what is going on and the potential of it. And this is why it's so important for me to talk about the hypernetwork technology. I think it's probably a good place to finish. If anyone has some question they would like to ask me, just email me. It's very easy to find me in Google, Lior Wolf or Wolf Tel Aviv University. Just find me, send me an email. I will be very happy to point you in the right direction, try to answer your question. If anybody would like to suggest a problem that is of interest to them and might interest us as collaborators, we would be very happy to hear about it. So thank you very much for your attention. I really enjoyed it. And please keep in contact. Let me know if you have any questions.
Thank you so much, sir. It was great having you with us today. May I thank the viewers as well for joining us. And thank you, Professor.
Thank you very much.